Hi, welcome to the new operating systems lecture. You can see this is a different platform than I have usually used for recording. It's basically a new machine, and I'm trying to figure out how to set up things on it. So I hope that this goes smoothly and does not become a disturbance for you guys. So today we're going to talk about threading. I think I actually thought that we will talk more about Linux today, but I realized that to get the most benefit, you guys probably need to get a bit more information on concurrency before we actually continue with our Linux lectures, as this will basically help you a lot in understanding what will be covered next when we talk about the Linux scheduler and these things. So we already covered theoretical scheduling to a very large extent. We are done actually with most of it except for multi-CPU scheduling that I promised to cover once we actually cover concurrency. So today we will actually start by talking about concurrency. And concurrency is basically also called multi-threading in some contexts and multi-processing in other contexts. And um, again, disclaimer, uh, not meant to basically make you guys lose focus or think that the book is bad. I'm just saying that this is in general a problem in teaching a course about operating systems, because operating systems are one of these religious parts of computer science. So different authors will have different approaches to things. um, So Three Easy Pizzas covers most of what we are going to teach in this course. I'm going to venture outside a bit, so do not get disturbed or do not get alarmed um, if you get like some slides that are not in the book. So we have talked about virtualization as an abstraction, basically a way for the operating system to provide an abstraction for you that it's not a single CPU, we have multiple CPUs, and thus you're able to run multiple processes. We have discussed how this is done using um, basically different scheduling mechanisms, FIFO, SJF, MFQ, MLFQ, and similarly other schedulers. Uh, Today we're going to talk a bit about how the operating system actually implements concurrency, implements the ability of the same program to run multiple things at the same time. And that is basically by adding another abstraction, which is the abstraction of threads. You have basically multiple threads instead of just one process. What does this mean? This is basically, I mean, we saw how um, a parent process can create a child process. Somewhere, sometime, uh, someone thought that maybe we just need yet another level of abstraction where a process itself is not just a single line of code. It's not just one single line of operations that happens sequentially. One process can be multiple threads. Basically, can be doing multiple things. This is a bit different, again, philosophically speaking, because implementation in real life is quite different. We'll cover a bit about that. Um, but theoretically speaking, this is basically like you have a process that can start different child processes that can start different child processes. These child processes can be just new programs that run, for example, because when we were talking about the Linux processes, for example, we talked about the init process that starts all other programs as children. So basically, when you start a shell in Linux, a terminal, you have started a process. And when you start new programs in this process, each program is started as a new process, as a child process to the terminal. And this is why, for example, when you close the terminal, after you have, I mean, you can try that. You can basically go to a terminal on Linux, type in Firefox or Chrome. I don't know what browser they use, and then Chrome will start or Firefox will start. And then if you close the terminal, then the terminal closes, and you'll find that the child process that was started, which is Firefox or Chrome, also gets killed. There are ways to make this child process live, which is basically running it with and at the end and no hop and stuff. But I mean, and if you don't do anything special, then your child process dies when your parent process dies. Now, people thought that each process might want to do multiple different things. So if you're talking about Firefox, for example, you might want to have multiple threads running in parallel. For example, for the same web page, for the same tab, you might be fetching data from different websites. So basically, that is what happens when you have embedded content in your page. What I'm saying, by the way, is just for you guys to understand. It's not what happens in reality. So do not go and argue with people that this is how Firefox works. No, I'm not saying that this is how Firefox works. I'm saying that one possible implementation of Firefox would be basically that when you start the process, Firefox now started, and you have a child process that is Firefox. Now you have a new tab, and now you're basically fetching data for the same page that you're going to show me. I mean, the operating system is going to show me. It's fetching data from different websites. So it's fetching, for example, embedded content from Twitter, embedded content from YouTube, and the text from the main website itself. So in that case, you might want to run three child processes, one fetching data from YouTube, one fetching data from Twitter, and the third one fetching data from the main website. In this case, these three processes, they actually share data and share files because they run in the same tab, but they have also different registers, different stacks, because each process, so if you're fetching video from YouTube, then you have your own registers and you have a stack that basically stores whatever video you have over there. They are sharing code. The three threads basically are sharing code, and each thread basically what it does is that it's fetching data from the internet. So they do share code, but in terms of the data that they have, they might have different data. And at the very end, the process that started these three threads will actually, for example, towards the end, basically show you everything in the correct place, because this is what what it is supposed to do. This is an example of how or what a thread can be. I'm not saying that this is how things are implemented. I am repeating that so that people do not take positions. So a thread's life. Now we had the PCB, the process control block. For a thread, for each thread, we have a TCB, which is the thread control block, which stores its state of performed computations. So how much data has it fetched from YouTube, how much data has it fetched from Twitter, how much data has it fetched from the main website, what processing does it need? Does it need to do rendering on the YouTube video? Does it need to render a photo from Twitter? Are there other images that it's bringing? Are there, for example, any ads that it needs to load, and so on? And there's the metadata for the management of the thread. Basically, each thread will have data, basically where it is connected, what it is doing, and so on. So if you look at the data, you'll have shared state, things that are shared between the different threads, like code, global variables, and heap. But you will have also a TCB which contains private data that is relevant only to a thread, like and that will actually contain like stack information, saved registers, thread metadata, because while the threads are running, each thread can be looked at as if it was a process, maybe. And in that case, each thread basically, I mean, you cannot have more than one thread scheduled at the same time on the CPU. Only one of them will run. And this complicates scheduling, as we will see when we get back to the multi-core scheduling, because now you have to schedule a process, and within a process if you have a pool of threads, you have 100 threads running, and you want to schedule these threads also. So you have you no longer have a single hierarchy of things. You have applications with multiple threads that are running in parallel, and the thread data will contain stack information that stores information of nested procedures, functions, methods that run in the thread. When a new thread is created, for example, a new stack is allocated for it, and the pointer to that stack is stored in the thread's TCB. So this is how things are. If you compare a process to a thread, then you will have, for a process control block that will have registers and stack and code, while a multi-threaded program will have multiple TCBs. Here is actually an interesting thing, and when we go back to our Linux lectures, we'll look at that in the PCB. The PCB, the process control block, basically links to the different TCBs. So it has, for each process, you will have basically you'll have sort of a pointer from the red to the blue that basically tells the operating system that, okay, this is a process, this is a multi-threaded process that has these different threads. So if you're looking at single-threaded versus multi-threaded address space, single-threaded as in program that has a single thread or have a single process, a process that doesn't have any threads basically. Multi-threaded is a process that have multiple threads. So if this is the memory, saying that just imagine that this is the memory, you will have the program code followed by the heap, okay? And the heap basically grows downwards, followed by the stack, which grows upwards. And of course, you can, after a while, you can start moving the stack and the heap. These memory allocation changes can be done, but in general, this is how things are implemented. For a multi-threaded address space, what you have is you'll have program code, a heap, then some free space for the heap to grow and for the stack number 2 to grow, and stack number 1 and some space for that stack to grow. So why do you use threads? I sort of said that. The first reason is that you want parallelism in the process itself. This is an example. You're writing a program that performs operations on very large arrays. For example, adding two large arrays together or incrementing the value of each element in the array by some amount. So if you have an array where you have its data structure, an array is a data structure basically. I hope you remember it from your data structures course, and if not, please look it up on Wikipedia. And you're basically adding values to each line to each array element. So in that case, you have, it's the same data structure, it belongs to the same process, but you're doing the same operation multiple elements. And if you have 10 cores, 12 cores, and there is nothing else to run, it would be a waste if you just run a single process that basically goes on the arrays one by one. It's also a waste to start a new process, in the sense that if you start a new child process, well, take this with a grain of salt, you consume more data because you start a PCB which has all the data of a process, while what you actually need is much simpler parallelism in your system. So this is the first reason. The second reason is more subtle, which is to avoid blocking programs due to slow I/O. So if a program is doing I/O and the program can proceed with doing other things while the I/O is being fetched. So you need the data, but you can do other things until the data comes. In that case, it's basically pretty stupid if you just block the whole program because, well, I/O is there. I have to block on I/O. What would be better if you have a single thread of computation that blocks on I/O, and the other threads which can continue in parallel can continue without actually having to block. And this is done in many modern server-based applications.